Okay, picking back up in 16.2 day 3 as we take a look at our second problem. It's actually the last full problem that we're going to be doing. We've got a force function defined to define that vector field. It's xy with I plus yz times vector j, zk, zx times vector k. The curve is given to us really not in a vector form, but it is given to us parametrically, and they're even giving us the boundaries that t must go between 0 and 1. So let's take a look at f of r of t if we were to apply this parametrization to our function f. We have x times y. Well, our x is going to be a t, so we'll have t, and then our y is going to be t squared, and that's really what we have for vector I. Vector j, we have y and z, so that's going to be t squared multiplied to t cubed. You can see that's our z component. That's the component for vector j. And then finally, as we move on to k, we have z times x. Well, z is t to the third. X, as we already saw, was just a t. So we could clean this up very, very quickly. And we could even write it in bracket form here, which I really like to do. This would be t cubed for our I component, t to the fifth for our j component, and t to the fourth for our k component. Now, of course, what you're also going to see is that your r of t, even though it wasn't written in this parametric form, you've got your x is t, your y is t squared, and you have your z is t to the third. R prime, if we just took our derivative here, we'd get 1, 2t, and 3t squared. Well, as we're going to calculate work, we're going to see that this is going to be the integral going between 0 and 1, because that's our t boundaries. And then we've got our f dotted with r prime, and our f, of course, is going to be our t cubed, t to the fifth, comma, t to the fourth. And we just found r prime, that's listed up here, that's our 1, comma 2t, comma 3t squared. And as we work this out, this dot product is actually pretty simple. And it's at this point where we're going back to an integral from last year. T cubed times 1, multiply your x components, you just get t cubed. T to the fifth times 2t, you'd get a 2t to the sixth. Multiply t to the fourth times 3t squared, you'd get a 3t to the sixth. And we actually do have two like terms here that we can put together. As we look at the last two terms here, that adds up to 5t to the sixth. Well, at this point, we just apply our fundamental theorem. We'll get t to the fourth over 4 plus 5t to the seventh all over 7. And we're evaluating that between 0 and 1. And of course, plugging in a 0, that's going to wipe out pretty nice and simple. You're just going to be left with 1/4 plus 5/7. And we could go ahead and do that little trick with arithmetic, as kids in Mexico have done, as I've been told. 7 times 1, it's like you're cross-multiplying. 4 times 5, you'd get a 20, but 4 times 7 is 28, leaving us with the work calculated to be 27 over 28. Okay, so as we go to our final page, just want to let you know that there is a connection between line integrals of vector fields and line integrals of scalar fields. As you begin to look at what we started off with today, even those boldface f and the boldface r, those are vectors. And you might wonder if there is some connection between going with this vector going to a scalar. And as you see us break things down, I think you can definitely anticipate that that is the case. As you really take the parametric forms of x, y, and z and plug them into f, you wind up with p times vector I plus q times vector j plus r times vector k. And if we're going to have our dot product with r prime, remember r itself really was just the parametric form, like we've got xt times vector I plus y of t times vector j plus z of t times vector k. And as we take our derivatives, very simply, we take our derivatives of our components. R prime is just x prime of ti plus y prime of tj plus z prime of tk. As you go ahead and do your dot product, multiply your x components together, you'd get p, which, by the way, in its parametricized form is p x of t, y of t, z of t, times an x prime of t. Do the same thing as you multiply your j components together. Q times y prime. Well, q in its parametric form here times y prime of t. Finally, take your r and multiply it to this k component over here, and you'd have r in its parametric form multiplied to z prime. However, what I hope that you remember is that when you had z prime dt, that was really dz. When you have y prime times dt, that was dy. And x prime times dt, that was dx. So what are we really seeing? We're seeing this right here, this vector form. It could be written in a scalar form, where you could say, here's your line integral of that I component of your force function, that's p in parametric form, dx. Your j component, which was q, multiplied to dy, plus your z component, which was r, multiplied to dz. So that's a very nice and simple way to take your vector form and write it in a scalar form. Okay, hope it's going well for you.